4th, one of the great railway bridges of the world. A Victorian-built masterpiece of engineering skill, it is still the biggest of its kind in all Europe. The queues of cars, longer each year, were a visible argument of the need for a new bridge, a road bridge. The best site for a crossing was, of course, already occupied by the railway bridge. The next best position lay about a mile upstream, where a submerged rock near the north shore and a shelf of rock running out from the south shore provided possible foundations. But the distance between these 2 points, about 2/3 of a mile of very deep water, demanded a bridge that would cross the channel in one mighty stride. Only a suspension bridge would answer this problem. The bridge designed for the crossing has a main span of 3,300 feet and 2 side spans, each of 1,340 feet. 2 slender steel towers rising over 500 feet above the 4th, and 2 reinforced concrete side towers standing on the river banks support a pair of massive cables which stretch over 7,000 feet from their anchorage tunnels driven deep into the bedrock of the north and south shores. From the main cables is hung the deck of the bridge, 16,000 tons of steelwork, carrying 2 roadways and 2 cycle tracks and footpaths. In 1958, the bridge has arrived at the site to take up the challenge. Work started on the construction of the 2 side towers. Their sturdy concrete legs, joined at the top by ribs, have to carry not only the ends of the side spans, but also the thrust of the main cables as they bend over the towers and down to the anchorages. The 4 anchorage tunnels, 2 on each side of the river, are driven down a 30-degree slope deep into the rock. On the north side, they are cut out of hard whinstone rock. On the south side, through bands of shale and sandstone. When complete, each tunnel is filled with concrete to form an immovable plug capable of withstanding the 14,000 tons pull of each main cable. The North Main Pier is founded on the Macintosh rock, first leveled off by underwater blasting and then surrounded by a coffer dam to enable the pier to be completed in the dry. For the South Pier, a different technique is used. A large figure-of-8 frame is built at a suitable site on the north shore and is then towed across the river to the position of the south. Sheet piles are driven around the frame to form a coffer dam. Inside this are built 2 60-foot diameter caissons, which are sunk under their own weight through gravel and boulder clay until they reach rock about 100 feet below the surface. The caissons are then filled with concrete to a level above high water to form the foundation for the tower. And now to erect the base sections of the steel towers. The first outer section is lowered and carefully positioned over the foundation bolts already set in the pier concrete. As all sections forming the legs of the main towers have been machined and pre-assembled in the fabrication shops to provide perfect fit, it is essential that the bases are set and leveled with the utmost accuracy. There can be no adjustment afterwards. As soon as each base is positioned, the massive foundation bolts are tightened down to clamp the base to the pier concrete with a load of about 2,000 tons. The bases are finally embedded in the concrete of the pier tops, ready for the erection of the towers. Meanwhile, the tower sections, fabricated in Glasgow, are being delivered to Drem, a disused airfield about 30 miles away from the bridge site. Here, the steelwork for the main towers and a great part of the deck will be treated to prevent rust and corrosion during the life of the bridge. Here also, the pieces will be collected and stored until required. Untreated structural steelwork is usually covered with rust or a hard, bluish-grey mill scale, and before any metallic protective coating can be applied, these deposits must be completely removed. For this job, a specially designed grit blasting chamber was installed at Drem Airfield. As each section is drawn slowly through the chamber, a high-velocity stream of chilled iron particles thoroughly clean the exposed surfaces. The spent grit is automatically recovered, cleaned, and stored for reuse. After blasting, the steelwork has a bright, silvery appearance with a slightly pitted surface. Thorough inspection follows, and the section is ready for zinc spraying. For this, another specially designed semi-automatic machine is used. In this process, pure zinc wire is fused at the nozzle of a pistol, and the molten particles projected by compressed air onto the steel. Here, two pistols, mounted on a movable carriage, travel back and forth across the surface, spraying on an even deposit of zinc not less than 3/1000ths of an inch thick. The coating is sprayed in a succession of horizontal bands. Any parts not reached by the machine are finished by hand. After further rigorous inspection, the metallized section is ready for painting. This coat is an etch primer, brushed on as soon as possible after zinc spray. A priming coat of zinc chromate paint follows, quickly and evenly applied by lamb's wool rollers. The third coat is a micaceous iron oxide paint, also rolled onto the surface wherever possible. Each of the three coats is applied to a strict timetable and carefully inspected at every stage. Where convenient, the fourth and final coat, of silver grey, is also painted on at Drem before the section is dispatched to the bridge site. The contact surfaces of the bolted connections are left completely unpainted. The treated tower sections are then taken by road through Edinburgh to the south side of the river, and on via Kincardine Bridge and Dunfermline for the north side. The first box section for the North Tower is delivered in August 1960. The 32-ton column of steel, over 40 feet long, is slowly raised by crane, swung round, and gently lowered, dowel pins guiding it into exact location. The erection of the tower is underway. The second section follows the first straight into its correct position. There is no doubt that it will fit. Each machined end is correct to a few thousandths of an inch. Next, the center box. 3 boxes, spaced 5 feet apart and connected together with stiffened plates, form one section of one leg of a tower. Each leg is made up of 11 such sections, stacked one above the other to reach a final height of over 500 feet above the river. As the tower rises beyond the reach of the crane at pier level, the sections are lifted into position by another crane, which climbs the tower legs stage by stage. Meanwhile, from Drem comes a steady flow of treated sections. The plant is working night and day on the components of both north and south towers. At the site too, the pace is quickening. Section after section is lifted up and bolted into place. No rivets are used in the design of the towers. All components prefabricated in the shops are of welded construction. All site connections are made with 2 types of special bolts. Close tolerance bolts in the vertical seams of the tower legs to ensure perfect alignment, and high-strength friction grip bolts in the cross bracings. In December 1960, a start is made on the south main tower. As soon as the first section is completed, the climbing structure is built. A rectangular platform of box girders embracing the tower legs. For climbing, the platform is pinned to 4 long steel links, hung down from the top of the newly completed tower section and passing through the corner compartments. In each of these 4 compartments is the hydraulic jacking gear for raising the platform from one operational level to the next. Jacks in each compartment, bearing against a pin through the link, slowly lift the platform. After rising 18 inches, a second pin is inserted through the link to hold the platform temporarily in its new position. All jacking operations are controlled from a central pump unit. Instructions to the men at the jacks are given through an intercom system. The screwed collars, a safety measure to prevent any accidental lowering of the jacks, are now released and the bottom pin removed. When all is clear, the main jacks are then reset and the lower pin replaced 18 inches higher. During the lifts, 4 clamps hold the platform to the tower legs. Each 18-inch lift takes 10 minutes, and a constant check is made to ensure that the climbing structure remains level. On reaching the new operational height, the structure is bolted and clamped to the top of the tower section, and the crane is ready to start work on the next lift. The climbing structure is also a safe working platform, giving protected access by means of auxiliary stages and gangways to all positions where men must work. A team of 22 men worked on each tower. It took 8 months through the stormy winter period with its bitter winds and icy cold to build the 2 towers. One thing bridge men do need is a head for heights. Even with a fast-moving hoist, it's a long way to the top. Now for the final job in erecting the towers. Capping the legs with the cable saddles. Massive castings to hold the main cables in a smooth curve over the tower tops. But already the engineers' thoughts are turning to the second phase of construction, the erection of the temporary catwalks right across the river, and the spinning of the main cables, the most unusual and perhaps the most difficult part of the job. By the end of June, both towers stood complete. The next task was to lay the 10 support ropes for each of the catwalks on the river bed, lift them clear of the water, and hang them over the tower tops. Each rope, in turn, is mounted on a pontoon moored to the north pier. The end of the rope is hauled back by winch line. It is then lifted to the top of the north side tower and secured. Next, a tug tows the pontoon across the river to the south pier as the rope is paid out and laid on the river bed. Not an easy job. Too much paid out and the rope might tangle. Too little and it would drag. Each rope has been pre-stretched and measured to exact length. Across the river are made, and 2 support ropes are unreeled each day, weather permitting. On reaching the south pier, a bight of rope is hauled onto the staging, and then the inner end is unreeled and taken up to the south side tower and attached to adjustment gear. By means of a derrick crane standing on top of each main tower, the first wire rope is lifted off the bed of the river, out of the water, and up to the tower tops, where it is clamped in its saddle. For the first time since the railway bridge was built, the 4th estuary is spanned. The second rope is lifted in exactly the same way, and so on until all 20 ropes hang across the 4th. Before the mesh floors of the catwalks can be built, the ropes must be correctly positioned and held parallel to one another. This is done by means of a light cross bridge slung between the two sets of ropes and pulled by winches out to the middle of the span. Then a small gang travel out in a work car suspended from one set of catwalk ropes to fix the cross bridge in its position. Another unusual means of travel for the bridge builders. With the support ropes stabilized, the construction of the catwalk floors starts at the top of each main tower. The pre-assembled wire mesh panels are laid across and loosely clipped to the ropes one behind the other to form trains of panels. On completion, each train is slid and hauled out to its position and secured. At the appropriate intervals, additional cross bridges are erected to prevent the catwalks overturning in high winds and to provide very necessary access between the walks. The assembly of the mesh trains is carried out at the same time in the main and side spans to maintain a balance at the towers. Months after laying the first rope on the bed of the river, the fourth can be crossed by foot from anchorage to anchorage. Meanwhile, preparations for spinning the main cables are underway on both sides of the river. In cable spinning, loops of wire are hauled over the catwalks from anchorage to anchorage by means of an endless aerial ropeway known as a tramway. The wires are then individually adjusted in each of the spans of the bridge to form groups of wires called strands. Both spinning and adjustment are carried out as a continuous process. Finally, the strands themselves are adjusted to their correct position in space as parts of the main cable. On the Fourth Road Bridge, cable spinning operations are controlled from the south side where most of the machinery is. The tramways, one above each catwalk, carry two spinning wheels which can be shuttled backwards and forwards across the river. "32,000 miles of wire are required for the two cables, enough to go round the world 1¼ times. Before the wire can be used for the cables, the coils, weighing about 1,000 pounds each, are joined together and wound on to large reels capable of holding 8 tons apiece. The ends of the coils are spliced by a specially designed steel sleeve. The whole assembly is squeezed in a hydraulic press to form a joint as strong as the wire itself. Each coil is led off a turntable, round a brake wheel to keep an even tension in the wire, and then on through a fleeter, which ensures that the wire is reeled in even layers, in much the same way as thread is wound onto a bobbin. The loaded reel is taken to the unreeling area behind the south anchorage to await its turn on one of the unreeling machines, which are arranged in two groups in V formation. the unreeling machines, the wires are led through the counterweight tower, another device to maintain even tension in the wires. Then on to the spinning wheel. The loaded wheel starts from the south anchorage on its journey north. Passing over the splay saddle, it moves on up to the side tower and then on to the main tower top. Small groups of waiting men, positioned at intervals along the catwalk, seize the wires and place them in temporary supports. The wheel is approaching the south main tower now. As it crosses over the top of the tower, the wires coming off the underside of the wheel, the dead wires, are placed straight into the cable saddle. The wires running onto the wheel, the live wires, are led over a train of small pulleys. Now the spinning wheel continues on its journey across the main span at a speed rapidly increasing to 700 feet a minute. Back on the south tower top, the dead wires are being clamped for adjustment in the south side span. Traveling at top speed, the loaded wheel passes the returning empty one at the mid-span point. On and up and over the north main tower, and then down towards the north side tower and anchorage. Each northbound wheel carries 4 loops of wire. Thus, each passage of a wheel from south to north means that 8 wires have been laid down over the catwalk. As soon as the spinning wheel reaches the end of its journey in the north anchorage, the wires are removed. The wheel is ready to return for reloading, and a signal is flashed to the control room on the south side. Meanwhile, the sequence of adjusting the wires in each span has reached the north anchorage. As each wire is placed around the strand shoe, it is clipped to a come-along winch and pulled up to its correct position. One by one, the 4 wires are carefully adjusted and clamped temporarily in place. Already, the next loaded wheel is traveling north. Back and forth, 16 hours a day, weather permitting. As spinning continues on one catwalk, adjustment of the previous 4 strands spun is underway on the other. Each strand in turn is shaken loose. Any wires lying too high or too low are corrected. The wires are then bundled together and bound to form a circular strand. The final adjustment of the strand itself can only be done at night, when temperatures are constant. At last, after nearly 9 months of working day and night, the spinning has gone on through the raw cold of the long winter, stopping only when the frequent storms sweeping down the river made work impossible. For the first time outside the United States, the cables of a major suspension bridge have been constructed by the cable spinning process. By now, the north and south approach viaducts are thrusting out from the high ground on both sides of the river to meet the main bridge at the side towers. But work on the catwalks is by no means finished. The 37 strands of each cable, built up in a hexagonal pattern, have to be squeezed to a compact circular formation of nearly 12,000 parallel wires. The compacting machine does this job. 6 hydraulic jacks press the wires into the final circular shape, roughly 2 feet in diameter. All the wires must lie neatly in place, parallel to one another. They are compacted every 30 inches and held by a temporary steel strap. So far, work has been concentrated on the construction of the cables. The next phase, the erection of the suspended structure, has already started. The first panels of the stiffening trusses are being built, cantilevered out on either side of each main tower, so that the erection cranes can be assembled ready to work out along the deck. Back on the catwalks, the cable bands have been clamped around the cables at 60-foot intervals, and the suspender ropes are being erected. Each suspender, formed of 2 bights of wire rope, is unreeled from the tower tops and slid down the catwalks, partially supported by work cars running on the tram support ropes. A difficult job, demanding the utmost care. These suspenders are up to 4 tons in weight and 300 feet in length. The twin ropes straddling the cable are finally lowered into the grooves in the cable band. The suspenders are erected, working outwards from the main towers, ready to support the deck structure. Either 4, 6, or 8 high-tensile steel bolts are used, depending on its position, to clamp the band tightly around the cable. The suspender sockets are connected to the top cords of the stiffening trusses, also by high-tensile steel bolts. By the beginning of 1963, the erection of the deck structure, the third and last main phase of the work, has begun. The general erection scheme is based on the use of 4 derrick cranes working outwards from the main towers, 2 advancing to meet one another at mid-span, and the other 2 traveling back towards the side towers. As each 60-foot panel of steelwork is erected, it is connected to the waiting suspender ropes. The derrick is then moved forward to build the next panel. Naturally, balance most important. The cranes must work outwards at the same speed to avoid undue distortions of towers and cables. At Drem Airfield, the metallization, painting and preparation of steelwork has gone ahead steadily. With no storage space at the bridge site, every single item must be dispatched to reach the right place at the right time. This is no easy task, with over 20,000 tons of steelwork to be handled through the processing plant and storage area. Arriving at the site, the steelwork is lifted up to deck level by cranes attached to the main tower legs, and then taken out to the working fronts on self-propelled bogies running on temporary rail tracks. Panel by panel, the deck structure continues to grow. 55 panels make up the main span, and 22 panels each side span. Many thousands of pieces have to be maneuvered and bolted into place more than 150 feet above the water. To give maximum protection for the steel erectors, nylon and terraline safety nets are slung from steel-framed carriages. As the bridge grows, the nets are moved outwards, so that the men at the erection fronts are always safeguarded. Section by section, cords, diagonals, cross girders and deck panels, the steelwork begins to take shape. And a rather odd shape at this point, with the main span deck first dipping, then rising steeply at the erection fronts. Due to this reverse curvature, the main joints in the lower cords remain open during this stage of construction. But the distortion will gradually disappear as more of the steelwork is erected and the weight becomes evenly distributed along the cables. One more panel to go. Just 60 feet to reach the side tower. Then work can be resumed in the main span. Meanwhile, longer and longer lines of cars await their turn on the crowded ferries during the summer holiday season of 1963. Next year, queuing will not be necessary. On the bridge, new aspects of the work have begun. Erection is again underway in the main span. Up on the catwalks, the cable band bolts have to be retightened to compensate for the stretching of the main cables caused by the load of the deck. Geared head wrenches are used to tighten each bolt to 70 tons tension. So that the clamping force in the bolt can be calculated, each is carefully measured by micrometer before and after tightening. In the north and south side spans, the concreting of the roadway deck slabs has started. The concrete, mixed in a central plant on the shore, is carried out along the deck on monorail bogies. A vibrating screed is used to provide an even surface for the asphalt topping. With the increasing weight of concrete in the side spans providing the necessary counterbalance, the two main span sections grow steadily until a few days before Christmas 1963, the gap is closed. On a cold winter morning with a freezing wind sweeping up the river, the last sections of top cord are lifted into place. At last, the north and south sections are joined together. An unbroken curve of steel spans the river. As the suspender structure is now hanging from the cables in its correct curvature, and the open joints along the lower cords have closed up, it is now possible to complete the bolting of the stiffening trusses. The welding together of the 8-foot wide steel panels forming the main span roadways follows erection. Automatic welding machines are used on the longitudinal seams. Up on the catwalks, one more job has still to be done: the wrapping of the main cables to protect them from corrosion. Two special machines are used to wind a galvanized wire tightly around the cables between the cable bands. The wrapping wire is laid over a thick coating of red lead paste. To complete the protection of the cables, the wrapping is given 4 coats of paint. At the same time, the suspender ropes are also painted. Using an air-operated cradle and 4 appliances called muckets, one man is able to paint the 4 ropes at the same time quickly and evenly. With the main span closed and the erection cranes dismantled, all attention is focused on getting the roadways ready for traffic. While concreting the decks continues in the side spans, the material bogies carry a steady stream of deck panels, crash barriers and grillages out along the main span. The remaining connections are being bolted up. The crash barriers are erected and welded. At each main tower, the expansion joints are constructed. These will absorb the movement of the whole suspended structure as it expands and contracts to changes in temperature and deflects under wind and traffic loads. At last, it is time to lay the road surfacing. For the main span, with its stiffened steel plate decking, mastic asphalt is specified to give the best protection against corrosion. This surfacing, 1.5 inches thick, has to be spread by hand over the entire length of the main span roadways. Light hand rollers press pre-coated chippings into the surface to give anti-skid protection. In the 2 side spans, however, where the decks are constructed of reinforced concrete, a 1.5 inch thick wearing course of hot rolled asphalt is laid and rolled by machine. At the same time, the bridge lighting is installed, the steelwork given its final coat of paint, and all temporary platforms and cranes at the main tower tops dismantled. Then, after 6 years' work, the bridge is ready for traffic. The great adventure is over. The bridge, which had first been proposed as long ago as 1740 and on numerous occasions during the past 50 years, now in all its slender elegance and strength across the Forth. On the 4th of September 1964, Her Majesty the Queen arrives to open the bridge to traffic. Everyone associated with the project is represented. Government and local authorities, the designers, the construction engineers, and the workmen. It is their day. Among the bridge builders are men who had helped create some of the world's other big bridges in Australia, India, New Zealand, Africa. Here, their worldwide experience has been combined to construct yet another of the great bridges for all time.
There's the Forth Road Bridge, which replaces Queen Margaret's Ferry. May this bridge bring prosperity and convenience to a great many people in the years ahead.
Buses and commercial vehicles can flow easily along dual carriageways, built to coincide with the opening of the bridge, from the city boundary of Edinburgh straight to the toll plaza at the south end of the bridge. Across the river and into Fife, where a further stretch of new motorways speeds the traveller on his journey north. The Forth Road Bridge, the largest suspension bridge in the British Commonwealth and in Europe, the 5th longest span in the world. Forth Road Bridge is built.